Welcome to Engineers Mindsets. So in today's class, we are going to be talking about capillarity. But before we do capillarity, let us understand the basic idea of surface tension. What is surface tension? Surface tension is simply a force that acts on the surface of a liquid, which causes the liquid to act like a stretched elastic skin. Okay, so mathematically, it can be defined as simply the force acting within a unit length of a liquid. All right, so surface tension, okay, gamma is simply force all over length, simply the force acting within a given length of a liquid. So we simply have this, okay? So we can simply relate that gamma is actually force per unit length, where this gamma is simply the coefficient of surface tension, and F is simply the force which causes the surface tension itself, and L is simply the length of the portion of liquid where this force is acting. So if we make F subject, the force causing surface tension becomes simply the surface tension coefficient multiplied by the length. So this is simply the force causing the surface tension. So it is simply if the force acting on the surface of every liquid that causes the liquid to act or behave like a stretched elastic skin. And examples could be found in when we see mysteriously see birds walking on surface of water without sinking. Even though the birds are more dense than the water, they walk successfully on the surface without sinking. It's simply because the surface of that water is actually acting like what, an elastic skin. So the birds will walk. Also, if you're able to make gently a needle which is even more denser than water, if you gently place it on the surface of the water, you can find out that in the absence of air or any other atmospheric condition, there is going to be a floating of that needle on the water. So those are all examples or reasons or cost. Those are all causes of what, surface tension. So it is simply a force which acts on the surface of a liquid to make the liquid behave like a stretched elastic skin. And mathematically, we have it to simply be what, force per unit length. And this force itself is simply what, the coefficient of surface tension multiplied by what, the length of the what, portion. Now, we wanted to talk about capillarity. What is capillarity? Capillarity is simply the rise or fall of liquids in a capillary tube. Capillarity is simply the rise or fall of liquids in a capillary tube. For instance, let's say we have a beaker. Let's say we have a beaker that contains water. Okay. Let's say we have a beaker which contains water, and then we introduce a capillary tube into this beaker. What happens now is that this water rises in size or in height. It rises in height in the capillary tube, and its surface forms what is called a concave meniscus. Okay, so the water, let's just simply call here this to be the height of the water in the capillary tube. Simply call this H. So this is actually what, a beaker, and this is water. Okay, and of course this is capillary tube. This is capillary tube. Okay, so we're simply saying that if you have water placed in a beaker, and then we put in a capillary tube inside the water, what happens is that there is a rise in what, level of water in the capillary tube. It increases more than the what, level of water in the beaker. Okay, so this is an idea that gives rise to what, surface tension. There is rise, but then again, let's also assume that we have this same beaker now containing what, a mercury. Okay, now containing mercury. Okay, and then we place our capillary tube inside this beaker. What happens now is that in the capillary tube, the mercury will reduce in size. Okay, the height of the mercury will actually reduce in the capillary tube. Okay, and its shape or the shape of the surface is actually called a convex meniscus. Okay, but the height of this mercury will actually reduce in size. Okay, simply call this H, which is the height of the mercury in the capillary tube. So different liquids respond differently towards different actions in the capillary tube. So as can be seen, for water, there was an increase in size in what, in the capillary tube when we dip the capillary tube into a beaker containing water. but also a liquid, which is now a mercury. When we dip the capillary tube, there is a reduction in the size or the height of the liquid. So this rise of liquid and then fall of liquid in the capillary tube is what we actually call capillarity. Is what we actually call capillarity. So I've said that. Okay. So the major reason why the height of mercury actually drops in the capillary tube is simply because mercury has a very strong cohesive bond or cohesive forces amongst themselves. So they tend to what clinch to themselves when they come into what a glass or a tube. They tend to clinch to themselves. So because the cohesive bond or cohesive force between mercuries are very strong, so they tend to clinch to themselves. Meanwhile, the reason why the level of water increases in a capillary tube simply because water has what is called a higher adhesive force. So the adhesive force between water and any other surface is very strong. So water tends to what clinch to the surface or clinch to the capillary tube and thereby increases in size. But this rise or this fall of liquid in the capillary tube actually gives rise to what is called capillarity. Okay, so we've said that the surface of the water in the capillary tube is called concave meniscus. Okay, while the surface of the mercury in the capillary tube is actually called convex meniscus. Now, between if I draw a tangent line here, let's draw a tangent line here. Okay, a line that cuts the surface of the water in the capillary tube, and then at the capillary tube let's also draw that same line here, a line that cuts the surface of the mercury towards the capillary tube. We are simply going to have that there's an angle formed here. Let's take this down a bit. There's an angle formed here. This angle can simply be called theta. Same thing here, there's an angle formed here. This angle can also be called theta. This angle that is made between the surface of the liquid in the capillary tube and then the surface of the capillary tube is actually called the angle of contact. We call that the angle of contact. Simply the angle to which the tangent of the surface of the liquid make with the capillary tube is simply called the angle of contact. Okay. Um, We've talked about surface tension as the force acting within a unit length of a given liquid, and we've established that the force is simply what surface tension coefficient multiplied by the length or the portion of the water in which this force is acting. Now, if we observe this capillary tube, two things play here. The first thing is that for this capillary tube to be in equilibrium, we have the force due to what surface tension, and also we have the weight of the fluid or the liquid involved in the capillary tube itself. For the liquid to be in equilibrium inside the capillary tube, two things play. The force of the surface tension force in the liquid must be equal to the weight of the liquid inside the capillary tube. Now, what is this surface tension force in the liquid? Okay, let's move over here now. We've established that surface tension force is simply what the coefficient of surface tension multiplying by the length. Okay, and if we observe the shape of the um, if we observe the shape of the surface of the liquid inside the capillary tube, I've said that the shape is actually what a concave meniscus, so which actually means it's a curve. We actually have a curve for the surface of the liquid inside the capillary tube. So it's actually a curve, or simply call it a sphere or a cycle. Okay. Therefore, the length of this liquid in the capillary tube, the length is going to be what? The length of a circle, which is simply the circumference of a circle, and that's simply giving us 2 pi times radius, which is simply the circumference of a circle. So, which simply means the surface tension force F, which acts on that liquid contained in the capillary tube, is simply equal to what? The coefficient of surface tension multiplied by the length, and the length now is 2 pi radius. Okay, so we can simply say F is equal to 2 pi r times coefficient of surface tension. So keep this equation aside. So this becomes the equation for the force of the force acting on the liquid present in the capillary tube due to what? Surface tension. I also said that for this liquid in the capillary tube to be in equilibrium, then there must also be a weight of the liquid. What then is the weight of this liquid? So weight of the liquid in the capillary tube, okay, weight of liquid. Okay, so of course we all know that weight is simply what? Mass times gravity. This is actually the formula for weight, mass and gravity. But we should also know that in this case, the mass of every liquid is as a result of what? The density present in the liquid, or as a result of the density of the liquid. So the mass of every liquid is actually as a result of the density of what? The liquid. So therefore, what then is density? Density of every liquid we know is simply what? Mass all over volume. So which means we can actually make mass subject, and that will simply give us density times volume by simply cross multiplying volume multiplies density. So you simply have that the mass of the liquid is simply density times what? Volume, which is density of the liquid times volume of the liquid. But then again, the shape of the liquid inside the tube is actually what? It can be either concave or it can be convex. So in general, we simply say it's what? A curve, or it's a cycle. So which means, and then it has a height h. Therefore, the volume is simply what? Area of the cycle multiplies by what? Multiplies by the height. That gives you the volume. Okay, so the volume of the liquid contained, um, volume V is now equal to what? Area of the cycle, which is simply pi r squared multiplied by what? The height of the what? The height of the liquid inside the capillary tube. So you simply have this to be pi r squared times height. That gives you the volume of the fluid, okay, or the liquid contained in the capillary tube. Okay, so this now implies that the mass of the fluid itself now is simply density times the volume of the fluid. Now simply give us pi r squared times the height, pi r squared times the height. Okay, so we can simply say that mass of the fluid in the capillary tube is simply pi r square h multiplied by density. So if we know this mass, it means now we can actually find the weight of the liquid contained in the capillary tube. And since weight is mass times gravity, this is now equal to mass is found as simply this pi r squared times h times density multiplied by gravity. So this simply gives us the weight. Therefore, this simply implies that the weight of the fluid is simply pi r squared times height times density times gravity. This becomes the weight of the fluid, or liquid present in the capillary tube. And I said that for there to be equilibrium inside the tube, it means the force or the surface tension force must be equal to what? The weight. For there to be equilibrium, the surface tension force must be equal to the weight. Okay, so the force simply gives us 2 pi r times the surface tension coefficient, and this is now equal to the weight. The weight is simply pi r squared times h times rho times gravity, which is simply this. So to actually obtain this capillarity action, like I said, capillarity simply means the rise or fall of liquid in the capillary tube. So it talks about the difference or variation in the height. So to obtain the height, h, we simply make h subject formula here by simply dividing through this equation by what? Pi r squared rho times g. So we simply have 2 pi r times surface tension all over pi r squared rho times g. So we simply have this. All right, so from here now, it is clear that pi, we can cancel pi. We have arrow here. Arrow can also go into one of these arrow. So you're simply left with 2 times surface tension coefficient all over arrow times density times gravity, where arrow is the radius of the tube, density, of course, density of the fluid involved, and then gravity remains 9.81. Okay, so which means this variation in height, okay, so which simply means the variation in height h is now equal to simply 2 times surface tension coefficient all over radius times gravity times height, okay, times density. So this becomes the variation in height, or the rise or fall in the capillary tube whenever a capillary tube is dipped into what? A beaker containing any form of liquid, either mercury or water. So we can always use this formula words to apply. Now, if there's an angle involved, like I said, there's always an angle of contact. The angle which the tangent of the curve of the liquid makes with the surface of the capillary tube is called the angle of contact. If there is an angle involved, then it simply means that this variation in height can simply be written as 2 times surface tension coefficient all over um, rho times gravity times density, okay, times cosine of the angle involved. So if there's an angle involved, we'll always have the surface tension height. We'll always have the height of variation in the fluid or in the capillary tube to simply be equal to this. So this is what we use. This is the formula we use to find the height of liquids present in a capillary tube whenever the capillary tube is dipped into a beaker containing any of the liquid. All right, guys, I hope you find this video very interesting. In the next video, I will start doing calculation using this formula and showing you how to apply them. All right, guys, thanks and cheers.